Hello and welcome to 2.5 Measures of Position. In today's lesson, we're going to be looking at Q1, Q2, Q3, box and whisker plots, and percentiles. Okay, so let's take a look at our first set of vocabulary. We start off with fractiles. These are numbers that divide an ordered data set into equal parts. Partition an ordered data set into equal parts. The most common fractile is the quartile. Okay, quartiles approximately divide an ordered data set into 4 quarters, 4 equal parts. You have the first quartile, Q1, about 1/4 of the data fall on or below Q1. Second quarter, Q2, about 1/2 of the data fall on or below Q2. Q2 is also known as our median. And third quarter, Q3, about 3/4 of the data fall on or below Q3. Okay, so here's a sample of finding quartiles. Each year in the U.S., automobile commuters waste fuel due to traffic congestion. The amount in gallons per year of fuel wasted by commuters in the 15 largest U.S. urban areas are listed. Find the first, second, and third quartiles of the data set. What do you observe? Okay, so from this data set, just like you find the median, you list the data from least to greatest. Okay, same thing you would do here. You identify the median. That's what I would recommend first. Get the median. And then for the lower half, you find the median of the lower half. Right, the median of the lower half, that's your Q1. And then for the upper half, the median of the upper half, okay, middle value. Again, you don't include Q2 in either of them, but it's the upper half. You find the median, that would be your Q3. Okay. Okay, so what does this mean? About 1/4 of the large urban areas, commuters waste 23 gallons of fuel or less. About 1/2 waste 25 gallons or less, and about 3/4 waste 30 gallons or less. Okay, using technology to find quartiles. The tuition costs in thousands of dollars for 25 liberal arts colleges are listed. Use technology to find the first, second, and third quartiles. What do you observe? Okay, so we could easily show this. Okay, so let's get the calculator up. Okay, so we go into stat. Okay, you're under edit. Go into L1. And now we would type in our numbers. Okay, so we have 50, 52, 51, 49, 52, 51, 27, 36, 30, 44, 40, 35, 40, 45, 34, 33, 23, 34, 27, 16, 18, 18, 35. Okay, so we go back to stat. Go right arrow, calc, one variable stats, L1, go down to calculate. Okay. So it gives us our mean, 37.04. Gives us our standard deviation for the sample, standard deviation for the population, n is 25, so that's good. And then here it gives us our least, our most, and it gives us our Q1, median is our Q2, which is 36, and Q3 is 48. Okay, so there's our Q1, 28.5, Q2, 36, and Q3, 48. Okay. Yep. And that's what we end up with. Same screen that we ended up with. Okay, interquartile range, IQR. It's a measure of variation that gives the range of the middle portion of the data, about half. This is the difference between the third and the first quartiles. Okay, so in short, IQR is equal to Q3 minus Q1. Okay, very straightforward. Q3 minus Q1. Okay, using the interquartile range to identify outliers. Okay, so here's our set of values, our steps to figure out, are there any outliers? What are they? Okay, so we first identify Q1 and Q3. We find the interquartile range. Multiply IQR by 1.5. Subtract 1.5 times IQR from Q1. Any data entry less than Q1 minus 1.5 times IQR is an outlier. Interesting. And then add 1.5 times IQR to Q3. Any data entry greater than Q3 plus 1.5 times IQR is also an outlier. Okay, so here we have a mathematical way of figuring out if a value is an outlier or not. Okay, no longer we go by the old eyeball test and we just look at the data. Okay, so here's the specifics. Okay, all tied to IQR. Okay, example, finding the interquartile range. Find the interquartile range of the data set from the first example. Are there any outliers? Okay, so we recall that Q1 was 23, Q3 was 30. So the interquartile range is Q3 minus Q1, which is 7. Okay, identify any outliers. First, note that 1.5 times IQR is 10.5. Okay, so that's important because that's what we're going to either add or subtract to the Q1 and the Q3. Okay, if we're trying to figure out the outlier on the low end, we're going to do 23 minus 10.5. Right, so 23 minus 10.5 would give us 12.5. And then 30 plus 10.5, that would give us 40.5. Okay, and so let's just recap what the rule was. Any data entry less than that Q1 minus the 1.5 times the interquartile range is an outlier. Any data entry greater than, okay, is an outlier. So, any data entry less than 12.5 is an outlier. Okay. And anything greater than 40.5 is an outlier. Okay, so less than 12.5 is an outlier. And then greater than 40.5 is also an outlier. Okay, so let's see what they say. Right, so they get the same thing. Okay, so looking back at that, at those values, 11 is an outlier. Right, 11 is an outlier. Very good. Okay, so in large urban areas, the amount of fuel wasted by auto commuters in the middle of the data set varies by at most 10.5 gallons. Notice that the outlier does not affect the IQR. Okay. Okay, box and whisker plot. Okay, so it's an exploratory data analysis tool, highlights important features of a data set, requires a 5-number summary. Right, it requires the minimum entry, Q1, Q2, Q3, and the maximum entry. Okay, pretty straightforward how we draw the box and whisker. Once you have your 5-number summary, you want to construct a horizontal scale, kind of like a number line, that spans the range of the data. So you must make sure you start from the low end and end up at the high end, from minimum to maximum. You plot the 5 numbers on the number line. You draw a box above the number line from Q1 to Q3. So at Q1, you draw the box going through. Draw your box from Q1 to Q3. And then where Q2 is, where the median is, you draw another line to show where Q2 is. Draw whiskers from the box to the minimum and maximum entries. So your whiskers are what connects the low end to the left side of the box and the high end to the right side of the box. Those are our whiskers. Okay, example from the first example. Okay, so this was what a typical box and whisker plot would look like from our first example. Okay, our minimum is graphed, maximum is graphed, Q1, Q3, and then Q2 is the median. The blocks represent about half the data, which are between 23 and 30. And that's a good way to remember it, right? The box in the box and whisker represents about half the data. Okay. Okay, so a little bit more interpretation. The left whisker represents about 1/4 of the data. So about 25% of the data entries are less than 23. Okay, good. The right whisker represents about 1/4 of the data also. So about 25% of data entries are greater than 30. Also, the length of the left whisker is much longer than the right one. This indicates that the data set has a possible outlier to the left. Okay, so that's a good indication. If one whisker is longer than the other one, the longer whisker indicates the data set has a possible outlier. Okay, good. Okay, percentiles and other fractiles. So quartiles divide data into 4 equal parts. If you have deciles, divides data into 10 equal parts. Percentiles divides data into 100 equal parts. Okay, and our symbols, quartiles go by Q's, deciles would go by D's, D1 to D9, and then percentiles go by P's, P1 to P99. Okay. Interpreting percentiles. The ogive represents the cumulative frequency distribution for SAT test scores of college-bound students in a recent year. What test score represents the 80th percentile? Okay, so 80th percentile. We cut across. We find the data value. Drop it down. Looks like between 1200 and 1300, so about 1250. Okay, so 1250 about. That would represent the 80th percentile. Okay, this means that approximately 80% of the students had an SAT score of 1250 or less. Okay, that's what that means. Percentile that corresponds to a specific data entry. To find the percentile that corresponds to a specific data entry, use the formula percentile of x equals number of data entries less than x divided by the total number of data entries times 100, and then round to the nearest whole number. Okay, so that's our formula for percentile. Number of data entries less than x. Okay. For the data set in the second example, find the percentile that corresponds to 34,000. Okay, recall that tuition costs are in the thousands of dollars, so 34,000 is the data entry 34. Begin by ordering the data. Okay, so here's the data ordered from least to greatest. Okay, here we have 34. We want the number of data values less than 34, right? So 1, 2, 3, 4, 5, 6, 7, 8. 8 values are less than 34. Okay, so now how many were there? There were 25 of these, right? So we have 8 divided by 25. And then we multiply by 100. So 8 divided by 25 is 0.32. So times 100, so this will be 32%. 32%, 32nd percentile, we should say. Okay, so what does that mean? That basically means the tuition cost of 34,000 is greater than 32% of the other tuition costs. Right, and that's the same interpretation we had. Okay, the standard score, we call it the z-score. It represents the number of standard deviations a given value x falls from the mean. Okay, so typical way how we do a z-score, we take the value minus the mean and we divide it by the standard deviation. And that tells us the number of standard deviations that a score falls from the mean. Okay, example. The mean speed of vehicles along a stretch of highway is 56 miles per hour. Yes, that's the mean. With a standard deviation of 4 miles per hour. You measure the speeds of 3 cars traveling along this stretch of highway as 62 miles per hour, 47 miles per hour, and 56 miles per hour. Find the z-score that corresponds to each speed. Assume the distribution of the speeds is approximately bell-shaped. Okay. Okay, so let's see if we can figure this out. We have the formula again is x minus mu over sigma. Right, so x minus mean over standard deviation. That will give us our z-score. Okay, so for our first one we would have 62 minus 56 over, and our standard deviation was 4. So that would be 6 over 4. That would be about 1.5. Okay, so about 1.5 standard deviations. This would be above the mean. Now the 47, let's figure that one out. 47 minus 56 over 4. Now 47 minus 56, that would be what? Negative 9. Negative 9 over 4. That would be negative 2.25. Okay, so that means for this speed, this would be 2.25 standard deviations below the mean. And then for 56, well, 56 is right on the dot with the mean, so that's going to be 56 minus 56, that'll be 0. So z-score of 0, right, this is not going to have any standard deviations above or below the mean. This is right on the dot of the mean. Okay, so this is how we would figure out our typical z-scores. Okay, let's compare with our answers. Right, we end up with the same values, 1.5, negative 2.25, and 0. Okay, and additionally we say that 47 miles per hour is unusually slow because its speed corresponds to a z-score of negative 2.25. Okay, in general, if the score falls within 2 standard deviations, that, remember from our empirical rule, within 2 standard deviations is about 95% of the data. So anything past 2 on the plus side or past negative 2 going in a negative direction, anything past the 2's we consider to be unusual score. Okay, let's take a look at comparing z-scores from different data sets. The table shows the mean heights and standard deviations for a population of men and a population of women. Compare the z-scores for a 6-foot tall man and a 6-foot tall woman. Assume the distributions of the heights are approximately bell-shaped. Okay, so 6 foot is what, 72 inches? Right, 6 times 12. Okay, so 72 inches for a man. Okay, let's say z equals 72 minus 69.9 over 3. Okay, if this would be about 0.7. And then for the woman, this would be z 72 minus 64.3 over 2.6. And this would be about 3.0. Oh, interesting. Okay, so 72 inch 6-foot woman is going to be rare because the z-score is 3. That's 3 standard deviations above the mean. Whereas 6-foot man has a z-score of 0.7. That's 0.7 standard deviations from the mean. So that's pretty common then. Okay, let's see how they analyze it. Okay, they got the same z-scores. Very good. Okay, z-score for a 6-foot tall man is within 1 standard deviation of the mean. This is among the typical heights for a man. Okay, good. The z-score for a 6-foot tall woman is about 3 standard deviations from the mean. This is an unusual height for a woman. And that's what we were saying earlier. Okay, so your usual scores just based off of the empirical rule. Within 2 standard deviations, that's 95% of your data. Anything outside that, we say unusual scores. If it's past 3 standard deviations in either direction, we would say that's very unusual scores. Because remember, within 3 standard deviations is about 99.7%. So if it's past the 3, that falls into the 0.03%. Or 0.3, we should just say 0.3% would be outside. Okay, so maybe 0.15% on this end and 0.15% on that end, but those would be very, very unusual. Okay, so let's see. And this will be the end of the lesson, okay, for section 2.5. Any questions, just send me an email or ask during class. Have a good day, have a good night. We'll see you soon.